This new section is entitled Testing a Claim About Proportion. The requirement to use this section is the following. There are a couple of requirements. The first one is, it must be binomial. It must be binomial. That is, it must be two outcomes. The second condition is that NP must be greater than 5, and I guess NQ must also be greater than 5. In fact, they can equal 5. Remember that mu is NP for binomial, and that the standard deviation is NPQ, the square root. Okay. It must be binomial, and NP and NQ must be at least 5. Must be 5 or more. And here's some notation. P hat is just x over n. And Q is 1 minus P, and I guess I should just state what P is. P is the population proportion. And while we're at it, P hat is the sample proportion. The number of successes divided in the sample divided by the sample size. And the most important thing is the test statistic is, as I noted in the last video, it's P hat minus P all over, kind of ran out of space, so I'll put it up here, the square root of PQ over N. PQ over N. Okay, and with that in hand, we're able to do some problems. But it must satisfy those two conditions. The second condition is actually two conditions. NP must be bigger than or equal to 5, and NQ must be greater than or equal to the number 5. Okay. So let's consider the following problem. In a survey of 703 selected workers, right there, I know that N is 703. In a survey of 703 randomly selected workers, 15.93% of them got their jobs through newspaper ads. Okay, 15.93% of these 703 people got their jobs from newspaper ads. Now, you want to consider hypothesis test, or consider hypothesis test that uses a 0.05 significant level to test the claim. So the claim is less than 20% of all workers in the entire field, the entire world, all workers get their jobs through newspaper ads. 20% of all workers get jobs through newspaper ads. Okay, so what is HO? Now, 20%, that's the proportion. So what we have is that P is equal to 0.20. 20% is 0.20. Now, what's the alternate? What's the claim? Claim is less than 20%. So the alternate will be P is less than 0.20. If the claim would have been less than or equal to, if it would have been that P was less than or equal to 20, well then I would have said the null hypothesis. Since that has equal, I can't use greater than, I can't use less than, and I can't use equal. That means I have to use greater than. Okay, but that wasn't the case. So let's get some picture going. We have, so one-tailed test. We want the 5%, the significant level, to be just in the left corner because it says less than 20%. So in here is 95%. This is 95% or 0.95. Now, if you go to your Z table, because n is bigger than 30, and let's just verify a couple of other things. NP, well, n is 703, and P, success is P. Success is you're getting a job from the newspapers, which is 1593. This is, I hope you see this is clearly bigger than 5. This is over 10%. This is 15 out of 100. It's actually a little bit closer to 16 out of 100. 15% is 15 out of 100. We're a little bit more than 15%. It's more than 15 out of 100. Out of 703, it'll be more than 15. Out of the first 100, 15 got a job through the newspaper. The second 100, 15. You're going to have 700s, each 15. You know, already just from 700, we have more than 5 workers getting their job from newspaper ads. Okay, what about NQ? So that worked. What about NQ? So it is binomial because either you do get a job from newspaper ad or you don't. Now we have to verify that NP is bigger than 5, and it is, and NQ, 703. And if, remember, P, that's P, plus Q should add up to 1. It's going to turn out that Q is that. Well, we're taking a bigger percent. Almost over 84% to 703 now. When we took 15% times 703, when we took 15% and we multiply by 703, we got more than 5. If you take more than 80% and multiply it by 703, if you take more than 15%, you're going to get more than 5. So the two criteria have been met. It is binomial, and NP and NQ are both bigger than or equal to 5. So now we're allowed to use this rule. Now, if you look up on your Z table where the left-hand corner is 0.05, you will learn that Z is negative 1.645. So now what we need to do is find the test statistic. Z is equal to p hat minus p divided by p cubed over n square root. P hat, they told us the proportion of the sample. It's right there. 15.93% of the people got their jobs from newspaper ads. 15.93. Minus, they claim that from the whole population is 20%. In the bottom you have P again, which is 0.20, times Q. Q is 1 minus P. 1 minus 0.2. $1 minus 20 cents, you all know, is 80 cents. Well, then ignore the units. The answer is 0.80. And this gets divided by n, which is 703. And if you were to do this arithmetic, you would compute or calculate that Z is negative 2.70. And negative 2.70 is to the left of negative 2.6. There it is. Right there, for argument's sake, is negative 2.70. Now, here's where it gets a little bit tricky. But I'll try to do it as clearly as possible. When it comes to the null hypothesis, when it comes to HO, you always must say reject. You reject HO or you fail to reject HO. Now, everything in here, even though some teachers would scream and holler, I call that the acceptance region. You would accept HO. Now, if we were in here, and I'll talk in a moment about how to be in here. If you're in there, you accept HO. Well, you can't say accept. That means you fail to reject it. If you accept something, then you must not have rejected it. If you go to the store, or if you go to the post office and they give you a package and you take it, well then you fail to reject it. You either could say, nope, I don't want that package, I'm rejecting it. Or you could not reject it. That is, accept it. Okay. Now the thing is, we didn't end up in here. Where do you end up is where the test statistic is. The test statistic was Z equals negative 2.70. That was Z. That's right here. That's in the reject region. So the answer is we reject HO. We reject HO. Now, when it comes to HA, either there's evidence to support it or there's evidence not to support it. Well, this is the region for HA. I'm going to support. There is sufficient evidence to support HA. That is, I do believe that less than 20% of the workers get their jobs through newspaper ads. I do believe that. And if you did many, many studies with 703 samples. You do many surveys with random surveys with 703 with a sample size of 703. 95 times out of 100, you would be correct in saying that there's evidence that HA is true. That you should go with the claim. Less than 20% of the workers get their jobs through newspaper ads. There's strong evidence to support that. So you always have to use the word reject when it comes to the null hypothesis. Either you reject it or you fail to reject it. Okay, how about this one? In a hybridization experiment, 8,023 offsprings P's were obtained. So we have 8,203 P's. Some of them are green, some are yellow. 24.94% had green flowers. The others had white flowers. Excuse me, not yellow, white. So that means that 75.06 were white. If you were to do 1 minus 2496, you would get what I said, 4057. Oh, this was a 4, excuse me. 10 minus 4 is 6. So you'd get 75.06 or white. Or if you wanted to deal in percentages the whole time, you could have said 100% minus 24.94%, and you'll get the same answer except it would be in percentage. 75.06%. That's the way. I don't know why that one didn't come up, sorry. And then I crossed it out to borrow. So you get 75.06 of these P's are white. Now suppose you want to do a hypothesis test at a 0.05 significant level. 0.05 level of significance. You want to test the claim. You want to test the claim that the green P's occur at a rate of 25%. So the null hypothesis would be that the proportion is 25%, which is 0.25. So the alternative would be, since they told us that it is 25%, then the alternative would be, it's not 25%. It's not 25%. It's not 0.25. Okay. So now we have our little bell curve. In here we put 0.05. Well, actually that's not true because this one is a two-tailed test. It didn't say that it's less than or more than. If it said it's more than, I would just use the right-hand tail. They said it's less than, I'd use the left-hand table. But this time, they said it's equal to. So I get to split the 5% from the 95. I get to split that 0.05 into 2 halves. Left tail gets 0.025. The right tail also gets 0.025. And it turns out that the z-score is 1.96. Negative 196 and positive 1.96. And in the middle, you still have your 95%. So if the test statistics ends up in here, if it ends up in here, then, quote, I want to accept HO. But you can't accept it. So you fail to reject it. And, you know, Z is equal to P hat minus P divided by PQ over N, the square root of the bottom. And P hat, that's from the sample. P is success. We're talking about green, getting green. So it's 0.2494. 2494. Minus P, which they claim is exactly 25%. And then you divide by P, which is a quarter, 0.25 times Q. 1 minus a quarter, 75 cents, 0.75. And you divide this by N, in the top left-hand corner, we have N is 8,023. And don't forget to take the square root of that bottom. And when you do that, you get negative 0.124. That's what Z is. And that Z is right there, negative 0.124. So we're in their acceptance region. So what we say is we fail to reject HO. So you can say that, so if you're, okay, so what's HA? It says it's not 0.25. But anything in here, we would say that it is 0.25. So there's not sufficient evidence to support the claim. And by the way, actually plus minus, this is called the, well, that's not true. Where are we? The negative 1.96 and the positive 1.96, the cutoff values, they're called the critical values. So basically, we reject the claim. We reject the claim that P is not equal to 0.25. Okay, so there's one last thing that we should talk about, and that's the claim. Do we accept the claim or not? The green peas, the claim is the green peas occur at a rate of 25%. But that means that that's in this region. That's in this region. So what we can say is there is not sufficient evidence to warrant rejection of the claim. we can't reject the claim. We don't have sufficient evidence to reject the claim. It seems like that what they're saying is true. It seems like what they are saying is actually true. Okay, let us try yet another problem. This time we'll talk about car crashes. The thing about statistics and probability textbooks and problems, they always talk about negative things. In a study of 11,000 car crashes, the N is 11,000, which, by the way, is bigger than 30. Just for the record, in the last problem, either you were green, the P was either green or white, which is binomial. And if you checked NP and NQ, they would have been 5 or more. Okay, so in a study of 11,000 car crashes, it was found that 5,270 happened within 5 miles of home. Wherever you lived, wherever these 11,000 people lived, one by one, they didn't all live in the same place. 5 of the 11,000 car crashes, 5,220 of the drivers were within 5 miles of their respective home, which of course means that 4,380 were not within 5 miles of home, because these actually add up to 11,000. At least I hope they did. Let's make this 52, I think. Yeah, that's better. So 5,280 were not within 5 miles of the home. If you take 11,000 and you take away the 5,720, you will get 5,280. Oh. Okay, 5,280. Now, this time we want to use a 0.01 significant level to test the claim. We have a claim that more than 50% of the car crashes occurred within 5 miles of home. Claim is that P is greater than, it says more than 50%. So it's greater than 50%. Okay, so HO would be P is exactly 50%. Since this does not have the equal sign, that's good enough for me to call it the alternative hypothesis. Okay. So maybe up here we have this. So it says greater, oops, let's move this away. Now, when we're talking about greater than 50%, so greater than, that's a right tail test. In the right tail, we put all of the 1%. 0.01 is 1%. So in here goes 99%. And if you look up this z-score, you would see that z is, let me take out my trusty table. It's going to be a high number. For 99%, I used to know this number. is 2.33. 2.33. Yeah. So right here, Z is 2.33. Now we find the test statistics. If it ends up to the left of 2.33, we fail to reject HO. That is, we're in the acceptance region here. If we end up over here, we in fact reject HO. Okay. So what is the test statistics? Z is equal to P hat. Remember that P hat is X over N, number of successes, and we're talking about the claim, talking about being within 5 miles of home. Over 50% of the people who had accidents were within 5 miles of home. So success is being within 5 miles of home. There were 5,720 of those out of 11,000. So that's exactly what goes here. 5,720 over 11,000. That's P hat minus P. Well, P is 0.5. 5,500 out of 11,000. And then we divide this by NP, or excuse me, PQ. Well, P is 50%, so Q must be the other 50%. And we divide this by N, which is 11,000, and we take the square root of that bottom. Crank this through on your trusty calculator, and you get 4.20, which is very large. It's very large z-score. Actually, it doesn't even matter whether it's large or not. What matters is it's bigger than 2.33. So this 4.20 goes to the right of our cutoff. This is our cutoff. Any test statistics that had z less than 2.33, it would be in this region. That's the good region for HO. So we would fail to reject it. But we're ending up here. So let me erase this. So what happens is we reject HO, point blank. We reject HO. And we say there is sufficient evidence to support our claim. Our claim was we're bigger than a half. Well, we were giving enough play where anywhere in here we would say it's a half. In this tiny area in the right, yep, it's bigger than a half. Our claim that P, in fact, is bigger than a half. Which is something reasonable, of course. More than half the people, half of 11,000 is 5,500. And this number is bigger than 5,500. So yeah, more than half the people did have accidents within 5 miles of home. So it's not unreasonable. Now, if just 1 more or 10 more had accidents near home, that might not be enough. But if it were less than 5,500, I'd be surprised if we did accept the claim. Because even our sample didn't accept the claim. Okay, that finishes the section testing a claim about proportions.